Hello everyone. So my name is Yue Yang. I'm currently doing a PhD at the University of Sydney School of Civil Engineering. Today, I'm very excited to share with you our latest research, which I've co-authored with William Umboh from the University of Melbourne and ARC Training Center of Optima, and my supervisor, Mohsen Ramezani. The title of our research paper is Freelance Drivers with a Decline Choice, Dispatch Menus in On-Demand Mobility Services for Assortment Optimization. So this paper has recently been published on the Transportation Research Part B. Okay, so let me start with the background and storylines of these papers. Yeah. Here, so I would like to introduce a very interesting video games. So when I was 10 years old, I played a video game named the Crazy Taxi. In these games, I played as a taxi drivers driving in an urban area. So what I have to do is I need to decide which passengers I would like to pick up, and I need to choose my own driving routes. I have to maximize my revenue during a limited game time. So in these games, the drivers have to make their own decision to maximize their revenue, to design their trajectories, to decide which passengers they would like to pick up. This paper, we shift our focus on the mobility on-demand services. As we all know, the numbers of MOD platforms like the Uber, Didi, they act as a bridge to connect the suppliers and with the customer. They offer taxi, ride-hailing, meal delivery, and logistics services. The most fundamental operational strategies for this platform is order dispatching. The widely used order dispatching policy is one-to-one dispatching, as showing the left figures. As we can see, like each drivers will be matched with at most one customers one time. So these platforms often penalize the drivers who reject the dispatching from platform. So such policies can negatively affect the driver's autonomy and satisfactions. As we reveal in our studies in translators, we show that the majority of suppliers in the MOD market are part-time and freelancer contractors. They have their own autonomies and preferences to decide where and when to work in the market. Yeah. So in these papers, yeah. So our idea is, what if we offer a menu of orders for these drivers to choose the orders that align with their preferences. This design can improve the overall matching efficiency for the platform, and can also attract more and more suppliers to join the market. But this strategy also requires the advanced algorithm design to measure the operational complexities and prevent the service inequities, such as the popular orders will be over-selected by the drivers in market, but we can only assign the orders to at most one drivers consequently. Yeah. So in the papers, we consider decision problems as what dispatch menus offer to which drivers. So to optimize these decision problems, we have to consider the driver's choice behaviors when they receive the dispatch menus from platform. Yeah, so firstly, we define the utility functions between the order and drivers and the UDO in these utility functions. So we account for the order types, order fares, total pickup times, and the special values of the order's destinations. And we also assume like each driver has a declined utility function for ignoring all the orders in the menus which denoted by the UDC, and consequently the choice behavior of each drivers can be modeled by by a linear a choice probabilities PDO. These probabilities will be determined by the utility functions we calculate from the last step. Okay, so then we move to the general formulation for our decision problem. So the object functions in this paper is to maximize the expected number of matchings in the market. So as we define the PX, the capital X is the menu dispatching decisions between drivers and orders. So here the capital PX equals to the sum of the capital PO. The capital PO is the probabilities of the order all set by at least one driver. And in these formulations, we also consider the four constraints. The first constraint, so we set the values of A to limit the number of drivers who can be used this order. And the second constraint, we have to also to set the value of B to limit the dispatch menu size for each drivers. Oh, okay. So after introducing the general models of problems, in this paper we consider two like problem scenarios. The first one is this one menu assortment. Yeah, in the scenarios we set A as one and set B as infinite numbers. In these scenarios, like each orders can be only in the menu of at most one driver, and each driver has an infinity size of the dispatch menus. Yeah, so then we can reformulate the object functions in the models. And these papers we have proved two proposition. The first we prove that our objective functions FD is a monotone decreasing functions, and the second proposition is that we prove the FD is some moderated functions. So consequently, the optimization problem in the disjoint menus can be equivalent to the submodular maximization problem. So the bulk problem can be solved by a continuous gradient algorithms developed in this paper. Okay, so then we move to our second problem scenarios, which we call the joint menu defense. In these scenarios, we see both A and B as infinity numbers. In these scenarios, we remove the limitation for the menu size for each drivers. We also let each orders can be viewed by the infinity number of drivers in the market. Yeah, so then we can reformulate the object functions. As we can see, there is no constraints in such problem. Yeah, so these papers we also we have the two propositions. So we found that the object function is no monotonic functions, and we also found that the object function is neither submodular or supermodular. Yeah, so these papers we propose a local search algorithm to serve the joint menu problem. Okay, so finally we move to our the last sections, numerical studies. Here in the sections we develop the simulators to verify and test our proposed method. So our simulators consist of three phases. The first phase is assortment optimizations. So we list a problem, we list a platform to make the the menu dispatching decisions based on the input demand, input supplies, and knowing the preference parameters. So after platform makes the dispatching decision based on our proposed method, yeah. So the second phase is selections. We simulate the drivers in the market to select the orders from based on what they receive from the platform. So after drivers make selections, So then we enter into the last phase, the operations. So like the orders will be assigned to the nearest drivers who take this order, and uh, the other drivers will the idle drivers will wait in the system for the future uh, dispatchings, and some orders will be canceled due to the impatient customers. And from the perspective of the demand data, so we utilize the real world data from New York Manhattan yellow cab taxi data. So we also consider a different type of customers. We introduce the meal delivery orders in the simulators. So here we consider some restaurant and some food trips based on our generation mechanism introduced in these papers. And from the supply side, so we consider a fixed number of drivers will be randomly distributed over the road networks and the operation time. Okay, so the simulation result is based on the 10 weekday simulation result, and we average like each indicators in the system. In the result, we introduce four benchmark method. The first one is the global menus, which means that all orders will be showing the menus in all drivers in market. Local menus mean that each orders will be shown in the menus of all feasible drivers with a specific pickup distance. And we also introduce two one-to-one dispatching method, MT, BT, and MTSB. Uh, and these papers, we proposed three methods. Like the greedy method for the disjoint menus and local search algorithm for joint menus, and we also propose a gamma greedy algorithm for joint menus. Yeah, so based on the result, we can show that our proposed method, like the SJLS, can achieve the highest number of matchings in the market and lowest number of cancellations in the market. So from the customer perspective, so we can say our proposed method can help the platform to reduce matching time and pickup time compared to other benchmark methods. Yeah, so from the perspective of the suppliers and drivers, so the first thing is that we can say our proposed method can help the platform to guarantee the revenue equities in the market. We can say so first thing we can say we can increase the drivers' revenues, and we can also reduce the standard deviations of the drivers' revenues among different drivers. Yeah. So another point is that we can reduce the number of the drivers leaving the market because we have already increased like revenues and also increase guaranteeing the revenues equities in the market. Yeah. Okay, so we also have like two very interesting observations based on our simulation result. The first one is matching frictions. So in the left figures, we present the number of demands and number of like idle suppliers in the market during the 3.5 simulation hours. The above for like our benchmark method, we show that numbers of demands and the numbers of idle drivers coexist in the market, which is so-called matching friction. Yeah. So, but in our proposed method, so we can see like the demand and idle drivers will not coexist in the market. So this demonstrates that like the our proposed menu assortment method can help the platform to alleviate the matching frictions in the market. Okay, so The second interesting observation is the revenues of the drivers in the market. Yeah, as we mentioned in the last slide. Yeah, so we can see our proposed like the menu assortment method can increase the average revenues for drivers, and at the same time we can see we can like the reduce the like the standard deviations of the driver revenues. We can achieve more even distributions of the driver revenues. This means our proposed method can guarantee the like the revenue equities in the market. Okay, so like this is the full content of these papers. Yeah, thanks for the attention. If you are interested in these papers, please scan the QR code to find the full papers. Thank you very much.